Hey, welcome back. In this video, we're going to discuss extremal functions of forbidden 0-1 matrices. This video will just cover some of the basic facts about this topic, and in the next video, we'll see some deeper results about 0-1 matrices. Before we get into any definitions or results, I'd like to talk about the motivation behind this problem. So the first motivation that I know of for extremal functions of 0-1 matrices is in robot navigation. So there's a mathematician named Mitchell who came up with a path minimizing algorithm for a robot to navigate through a rectilinear grid. And the grid has obstacles. And Mitchell used extremal functions of forbidden 0-1 matrices to find an upper bound on the running time of the algorithm. So that's the first application that I know of for this problem, and one of the more interesting applications. Another really interesting application to me is this problem, which was posed by Erdős and others, many others. And the problem is to find the maximum number of unit distances that you can have in a convex n-gon. So first, let's talk about what this means. So let's say we had a triangle. So that's a convex polygon. And if all of the sides were length 1, that would have a total of 3 unit distances. Similarly, we could take a unit square where all the sides have length 1. That would have 4 unit distances. We can continue it like that for any polygon. There's other ways we can have unit distances. So maybe we have one vertex over here, and then it has unit distance to all the other vertices. So all the other vertices maybe are on the circle, which is centered at that vertex of radius 1. So the question is, how large can you make the number of these unit distances in any convex n-gon? And the best known upper bound for this problem is big O of n log n. And the best known lower bound is omega of n. So there's only a linear lower bound and a big O of n log n upper bound. So the lower bound and upper bound are pretty far apart. And this has been the state of them up to a constant factor for decades. And this upper bound is proved using 0-1 matrices. The lower bound is just a construction. In fact, the construction that we drew here and here and here, the generalization of that gives that lower bound. Another interesting application of 0-1 matrices is to solve a famous conjecture. The solution to the conjecture was found, I think, around 15 years ago now, but it was known as the Stanley conjecture. And it was a conjecture about the number of permutations that avoid a given fixed permutation. And we'll discuss that a little more in the next video. And what's interesting about the Stanley-Wolf conjecture is that you can find a bound on this quantity, this number of permutations, using upper bounds on extremal functions of 0-1 matrices. So you can reduce it from a problem about permutations to a problem about 0-1 matrices. So now that we've seen a few applications, and we'll go into some more details with the Stanley-Wolf conjecture next time, let's start getting into the math. So first definition, a 0-1 matrix. This is just a matrix with all the entries equal to 0 or 1. So for example, the 2x2 identity matrix, this is a 0-1 matrix. Here's another 0-1 matrix. Here's one too. So is this. So all zeros or all ones would be fine. And we say an m by n matrix, that's a matrix with m rows and n columns. So the number of rows comes first and then the number of columns. So for example, the one I drew here is a 2x3. And all the others that I drew were 2x2s. We say that a 0-1 matrix A contains a 0-1 matrix B if some submatrix of A either equals B or can be turned into B by changing some ones to zeros. So let's say the matrix that I just drew in the top left, let's call that one the A. And I'm going to draw some others. Maybe a couple others. Okay. So we have this definition of containment, and we say that if A does not contain B, then A avoids B. So the examples that I drew at the top, let's look at whether A contains or avoids each of these examples. So first, with A and B, does A contain or avoid B? Well, we can look at this submatrix of A, which has these two rows and these two columns. So last two rows, last two columns, and that submatrix of A equals B. So A does contain that B. Now let's look at C. So we can actually take the exact same submatrix. So we can take the last two rows and the last two columns, and then we can change this one to a 0 and this one to a 0. So you're allowed to change some ones to zeros if you need to. And that gives us a copy of C and A. So A also contains C. And then let's look at the last example. So we've contained B, we contain C, but does A contain D? And we can see that the only way for A to contain D would be if the submatrix was the whole matrix A. And we would need that submatrix, the whole matrix A, to be able to be turned into D by changing possibly some ones to zeros. And the problem is that we need ones here and here to have D in A. And since there's no ones there, it means that A avoids D. So A does not contain D, A avoids D. We can also see, if we look at D, this D right here, we can say avoids B. Because no submatrix of D is equal to B or can be turned into B by changing some ones to zeros. And that's because any 2x2 submatrix of D is going to have at least 2 zeros. It definitely can't have 4 ones, which B has. We can note, however, that D contains C. So for example, if we look at the first 2 rows of D and the last 2 columns of D, that gives us a copy of C and D. So now that we've seen some examples of containment and avoidance, here is the 0, 1 matrix extremal function. So given any 0, 1 matrix P, we define the extremal function Ex of m comma n comma p. So this extremal function has 3 inputs, m, n, and p. And it's defined to be the maximum possible number of ones in any m by n 0, 1 matrix that avoids P. So this 0, 1 matrix that avoids P has m rows and n columns. We'll be focusing on the square version of this extremal function, where the number of rows and the number of columns is the same. This is the most well-studied version of the extremal function. So specifically, we'll be focusing on the extremal function Ex of n comma p, which is equal to Ex of n comma p. So we use this shorthand with only 2 inputs to represent the square version of the extremal function. So now that we've covered some definitions and examples, let's look at some basic facts about the extremal function. So the first basic fact I'll mention on this slide right next to the definition. So we have Ex of m comma n comma p is the maximum possible number of ones in an m by n 0, 1 matrix that avoids P. And Ex of n comma p is going to be the maximum number of ones in an n by n 0, 1 matrix that avoids P. So we can see, since an n by n 0, 1 matrix, it has a total of n squared entries. So the most possible number of ones it could have, regardless of whether it avoids P or not, is going to be n squared. So we get a trivial upper bound of n squared on this extremal function, ex of np. So that's our first basic fact about it. And here's another basic fact. So if P contains Q, then we can say always that the extremal function ex of np is at least the extremal function ex of nq. And that's because if we had some n by n 0, 1 matrix A that avoids Q, then that implies that A must also avoid P, since P contains Q. And we can take this A matrix to have ex of nq ones. Here's another basic fact. Suppose you have some matrix P So here's P. And then you rotate it 90 degrees. Let's call that one P prime. Or actually, we'll call it Q. Then we can say that EX of NP is equal to EX of NQ. And that's because if we have some A that avoids P, we can do the same rotation on it that we just did to P to get Q. So we just rotated A. We'll call that one B. And B must avoid Q. Because if B contained Q, then that would mean that A would have had to contain P, but we assume that A avoided P. And we can take that A to have EX of NP1s. So that gives us a matrix that avoids Q, an n by n matrix that avoids Q with EX of NP1s. So we know EX of NQ is at least EX of NP. And then we can apply the same argument with the rotation in the opposite direction to get that EX of NP is at least EX of NQ. So they're the exact same value. A rotation does not change the value of the extremal function. Similarly, we can reflect vertically or horizontally. So for reflecting vertically or horizontally, we can look at it like this. So we have our matrix P right here. And here's a horizontal reflection. And if that's Q, we can see that the extremal functions are the same here. So if A avoids P, then we can just do that same reflection. And this new matrix B right here, obtained by reflecting A, that one must avoid Q. And it must avoid Q, or else A would have contained P. And then we can do the exact same thing, starting instead of a matrix that avoids P, starting with a matrix that avoids Q. So we see that both EX of NP is at least EX of NQ, and EX of NQ is at least EX of NP, because if we have any matrix with EX of NP1s that avoids P and it's an n by n matrix, we can turn it into a matrix with EX of NP1s that's an n by n matrix that also avoids Q, and vice versa. So they're the exact same extremal function. So if you reflect horizontally, it does not change the extremal function. And the argument is analogous for reflecting vertically. And I'll also mention some other facts. So here's a basic one. If we consider the 1 by 1 0 1 matrix with just a single entry equal to 1. So this matrix has a single row and a single column. And we can see that the extremal function of that matrix is going to equal 0. And that's because if you have any ones in your matrix, then you would contain this 1 by 1 matrix with a 1. You can't have any ones or else you contain it. So to avoid it, you can only have 0 ones. So the extremal function is 0. So this is the smallest that the extremal function can be, because you can't have fewer than 0 ones. Can't have a negative number of ones. Here's another pretty simple extremal function. If we have this matrix, which is a 1 by 2 0 1 matrix, a matrix of all ones, its extremal function is n. We can see this in two parts. So the first part, we'll see why it's at least n. To see that it's at least n, we just have to construct an n by n matrix with n ones that avoids this matrix. So we can take the n by n matrix whose first column is all ones, and the rest of the entries are all zeros. So that matrix has a total of n ones, and it avoids this matrix because it has no row with 2 ones. Now for the upper bound, so we proved this. So the question mark is resolved, but here, this question mark, we still need to resolve. So y is less than or equal to n. So if we had more than n ones, so if at least n plus 1 ones, then some row with at least 2 ones by the pigeonhole principle, because there's only n rows. And if we had at least n plus 1 ones, we would have to have some row with multiple ones. If you have a row with multiple ones, then you would contain this pattern. So having a row with multiple ones means that you contain the 1 by 2 matrix of all ones. So that would be a contradiction. So that means that the extremal function is at most n and it's at least n. So it has to equal n, since it's both at most and at least n. We can also argue the next bullet really similarly. So the next bullet is just the next matrix in this sequence. So if we take this 1 by 3 matrix of all ones, its extremal function is equal to 2n. We can see that it's less than or equal to 2n because by pigeonhole principle, if we had at least 2n plus 1 ones, that would imply there would be some row, and that row would have at least 3 ones. So we just use the pigeonhole principle there. We'd have some row with at least 3 ones, and that would mean that we would contain this pattern. And we're trying to avoid that pattern. So we can't have at least 2n plus 1 ones. We must have at most 2n ones. We can also see that the extremal function is at least 2n. In order to see the extremal function is at least 2n, we just need to construct an n by n 0, 1 matrix that has 2n ones and avoids this 1 by 3 matrix of all ones. So we'll take the one that we drew last time with a single column of all ones on the left, and then we'll add a column of ones next to it. And then the rest of the columns will be 0. So this matrix has a total of 2n ones. It's an n by n matrix, and it doesn't have any row with 3 ones. So it avoids this 1 by 3 matrix of all ones. So that gives us the lower bound, and we have a matching upper bound of 2n. So it tells us the extremal function is equal to 2n because we proved both parts of the bound. So for the next fact, let J sub S comma T denote the S by T matrix of all ones. So for example, J2, 2, this is just the 2 by 2 matrix of all ones. J of 2 comma 3, this is going to be the 2 by 3 matrix of all ones. And J of, let's say, 3, 1, this is going to be the 3 by 1 matrix of all ones. So here's a problem for you to think about. So see if you can prove or disprove with a counterexample that EX of n comma J sub 1 comma T is equal to EX of n comma J sub T comma 1 is equal to T minus 1 times n for each T greater than or equal to 1 and n greater than or equal to T minus 1. This problem has 2 parts. So I probably should have labeled this as part A. So there's part A. And then for the same problem, here's part B. So part B, just tell me the other side of it. So part A covers n greater than or equal to T minus 1. Tell me what happens for n less than T minus 1. What's the value of the extremal function? So that's part B. So let's look at a few more facts about the extremal function. So I claim if we have a 0, 1 matrix P and it has at least 2 ones, then the extremal function EX of n comma P is at least n. We can see this by considering a couple of cases. So case 1, we can say P has 2 ones in different rows. So if P has 2 ones in different rows, we can take an n by n 0, 1 matrix which has only a single row of ones, and all the rest of the rows are all zeros. And that matrix must avoid P. Because P has two ones in different rows. And that matrix has all its ones in the same row, so it can't contain P. So that covers case 1. Case 2 will be anything that's not covered by case 1. So we know that P has at least two ones. If P does not have two ones in different rows, it must have two ones in different columns. So that's case 2. P has two ones in different columns. And in that case, we can consider a different n by n 0, 1 matrix. It'll have a column of all ones, but then the rest of the columns will be all zeros. And this one avoids P in case 2 because P has ones in different columns and that matrix has all of its ones in the same column, so it can't contain P. So this is how we see that the extremal function of n comma P is at least n as long as P has at least two ones. Here's a problem for you to think about. This is a very similar kind of problem. And see if you can either prove that this statement is true or find some simple counterexample to disprove it. So prove or disprove that if P is a 0, 1 matrix that has a 1 and at least two total entries, then the extremal function of ex n comma P is at least n. So that one is for you to think about and see if you can either prove it a similar way to the one we just did there, or maybe it's not true and see if you can find a very small counterexample. And here's another basic fact about the extremal function. Suppose that P is a 0, 1 matrix that has no rows or columns with all zeros. Then I claim that the extremal function of ex n comma P is less than or equal to the extremal function ex of m comma P for all m greater than or equal to n greater than or equal to 1. And we can see that. So we can suppose that A is an n by n 0, 1 matrix. We'll suppose that it has ex of np1s and it avoids P. We'll take A and then we'll add on a new row and column of all zeros. We'll call that A prime. And we will keep on adding new rows and columns of all zeros. To make A prime an m by m 0, 1 matrix. So A is n by n, m is greater than or equal to n. So to get an m by m 0, 1 matrix, we can just add rows and columns of zeros to A until we get an m by m matrix. I claim that A prime still avoids P. And why is that true? Well, if A prime contained P, then the copy of P cannot have all been from the submatrix of A prime on A. So the copy of P can't all have been from this part because we assume that A avoids P. So if the copy of P was from that submatrix of A prime that was on A, then we would have known that A contained P, which would contradict our assumption about A. So the copy of P in A prime must use one of the new rows and columns. And that means the copy of P would have to have an empty row or column. So the copy has a row or column full of zeros. And the problem with that is that we assume that P is a zero matrix that has no rows or columns with all zeros. So P doesn't have any row or column with all zeros, but this copy of P has some row or column of all zeros. And that would be the contradiction. So if A prime contained P, we get a contradiction. That means that A prime avoids P. So we found an m by m 0-1 matrix with the same number of ones as A, and it still avoids P. And that means that EX of MP is at least EX of NP. And I just want to note that the fact that A prime avoided P, it was important here that P had no rows or columns with all zeros. So this assumption, no rows or columns with all zeros, that was the crucial assumption with this construction. So on the next few slides, we're going to consider some more interesting kinds of operations that you can do on 0-1 matrices. And these operations do not substantially change the extremal function of the matrix that we apply them to. So for example, this first operation, I call it adding a new last column with a 1. So this operation, I'm going to describe it in words. I'm also going to draw a picture. In some ways, I feel like the picture is a better way to think about it. So we'll say that P is a 0-1 matrix that has a 1 in row R in its last column. So I'm going to draw P here. Just have a 1 somewhere in this last column. Suppose it's in some row R. Then we define a new 0-1 matrix. We take P and then we add on a new column. The new column only has a single 1. All the other entries are zeros. And that 1 is next to the 1 in row R. I claim that the extremal function EX of NP is less than or equal to the extremal function EX of NP prime, and that's less than or equal to the extremal function EX of NP plus N. The interesting part really is the right side. So we added on a new column. The new column had a new 1 on it, so we added on an extra 1 to our pattern. Doing this operation, it only changes the extremal function by at most plus n. So let's start out by quickly discussing why the left side's true. The left side is immediate from a fact that we discussed earlier, and that's the fact that if we have some 0-1 matrix Q that contains another 0-1 matrix P, then EX of NP is less than or equal to EX NQ. In this case, the P prime that we constructed contains P. So EX NP is less than or equal to EX of NP prime. Now let's focus on the more interesting side, which is the right side. So for the right side, we will suppose that we have an n by n 0, 1 matrix. We'll call it A prime. And it has ex of n p prime 1s, and it avoids p prime. So I'm going to draw an example of A prime to illustrate the operation that we're going to do on it in the next bullet. Okay, that's A prime. That's just an example of A prime. That's a 5 by 5 A prime, so that's for n equals 5. And here's the operation we're going to do on A prime. We're going to make a new 5 by 5 matrix, in other words, a new n by n matrix. We'll call it A. And it's obtained from A prime by changing the last one in each row of A prime with a 1 to a 0. So for the A prime I drew up there, the new A would be this right here. So first row, 4 of the ones stay the same, but the last one turns to a 0. Second row, first 4 entries are the same, last entry is 0 now. Third row, first 4 entries unchanged, last entry is 0 now. Second row, just the third entry changes to a 0. And the final row, the fifth row, so that would be A for that example. Here's another smaller example. If we have an A prime here, here would be the A. So top row, we just change the last entry to a 0. Second row, we change the second entry to a 0. Third row is unchanged because it didn't have any 1s. So those are just 2 examples of this operation. And I claim that A avoids P. Why must A avoid P? Well, if A contained P, then let's draw a picture of that. So we have A here. So here's A. It has some copy of P in there. Here's P. And we know the copy of P, it has that 1 in row R. So in that submatrix of A, in that copy of P in that submatrix, there is the 1 in the copy, the 1 in row R of P. And we know that A, when we created A from A prime, we changed the last one in each row with a 1 to a 0. We see that this row right here in A, it has a 1. So it means that in the original matrix A prime, that row must have had some 1 to the right of this one. So there's some 1 over here. And that, if we take the copy of P with that extra 1, that gives us a copy of P prime. That's a copy of P prime in A prime. So this 1 right here, that 1 is in A prime. So not necessarily an A. So that is possibly the one that we removed from A prime to get A for that row. But we know that that 1 must be an A prime. So that means that there's a copy of P prime in A prime. if we had a copy of P and A. And a P prime in A prime would be a problem because we assume that A prime right here avoids P prime. So this would be a contradiction if A contained P. So we know that A has to avoid P. And since A avoids P, and A is an n by n 0, 1 matrix, because we obtained A from A prime just by changing some ones to zeros, and A prime was an n by n 0, 1 matrix. So that means the number of ones in A is at most EX of NP. Because remember, EX NP right here is the maximum possible number of ones in an n by n 0, 1 matrix that avoids P. And A right here, it avoids P, and it's n by n. We have another fact relating the A and the A prime. We can say that the number of ones in A prime is at most the number of ones in A, but then plus n. And that's because to get the A from A prime, all we did was delete at most one from each row of A prime. And A prime has n rows. We removed at most a single one from each row. So we only removed at most n ones in total from A prime to make A. And we can combine the last two bullets there. That tells us that the number of ones in A prime is at most EX of n comma P plus n. And we can go back to this bullet where we defined A prime. We said that A prime had exactly EX of n P prime ones. So that tells us that EX of n P prime is at most EX of n P plus n. And that gives us the inequality that we wanted. So now that we saw a basic operation that we can do on 0, 1 matrices that doesn't substantially change their extremal function, here's a problem for you to think about. And I'll mention some hints about this problem. So it's about a different operation. So instead of adding a column at the end with a single 1, we're now adding an interior column with a single 1. So P is a 0, 1 matrix, and it has a 1 in row R in both columns C and C plus 1. So here is P. And then we have a 1 here, a 1 here. These columns are columns C and C plus 1. And then we define this new matrix P prime. And P prime is like P, but with an extra column now. So we insert a new column between column C and C plus 1 of P. This column has all zeros, except for a 1 in row R. And that's P prime. So P prime just has an extra column that we added to P, but that column is between these columns, C and C plus 1. So I claim if we add this new column with a single 1 between column C and C plus 1, where its 1 is in the same row as the ones that we denoted in column C and C plus 1, then the extremal function of this new 0, 1 matrix P prime is less than or equal to 2 times the extremal function of P. So we can say EX of n comma P is less than or equal to EX of n comma P prime is less than or equal to 2 times EX of n comma P. The left side, since this is a problem, it's a problem for you to think about, I'll leave the left side to you. I think you can get that left side. For the right side, let me give you a hint, kind of similar to the construction that we did on the last slide. It's different, but in a way it's analogous. So here's the hint. Suppose that we have an n by n 0, 1 matrix with ex of n p prime ones, and it avoids p prime. So I'm just going to draw a matrix here, and we're going to look at an example of the operation I'm about to define. And here's the operation. We'll take that matrix A prime, and then we'll change every other one in each row with at least 2 ones to a 0. And we're going to start with the second one in each row, not the first. So let's look at that A prime I drew, and then look at what happens to it. What's the A that we get? So A, from that A prime, we're going to change every other one in each row to a 0, but we're starting with the second one. So we keep the first one, but then we change that second one to a 0. So that first row, instead of a 1, 1, 1, 1, 1, we got a 1, 0, 1, 0, 1 now. The second row, we have a total of 3 ones. So the first one stays the same, but that second one we got to turn to a 0. Third row, first one stays the same, but that second one becomes a 0. Fourth row, first one the same, second one is 0 now. And that last row, it only has the single one. We don't change it. So that's just an example of this operation, which I claim will be useful for solving the problem. So see if it's possible to use this construction from A prime to A to show that this upper bound, the one on the right, is true, using some similar logic to what we did on the previous slide. So before we get to the end of this video, let's discuss one more operation that allows us to show that a more complicated 0-1 matrix has an extremal function which is on the same order as a much simpler matrix, like the operations that we just discussed. So we started with simpler matrices. We made them more complicated by adding new columns and extra ones. And in general, these operations, that's what we're doing. We're showing that we can find bounds on more complicated matrices, matrices that are larger or have more ones, by using bounds that we know on some simpler 0-1 matrices. So here's another one like that. In this one, we start with 2 simpler matrices, and we make a more complicated one by joining them together. So we suppose that P is a 0-1 matrix, and it has a 1 in its bottom right corner. So I'm going to draw a P up here. We also have another 0-1 matrix Q, which I'm going to draw. And it's going to have a 1 in its top left corner. And we're going to join them together to make a new 0-1 matrix, a larger one called R. So we'll obtain it by translating P and Q. So there's the P right there. And we'll translate them so that they overlap in that corner. So here's the Q. And then everything else is zeros. So we have a copy of P in the top left. We have a copy of Q in the bottom right. And in the top right and the bottom left, we have all zeros. So outside the copies of P and Q, all the other entries in this matrix R are zeros. And I claim that the maximum of EX of n comma P, EX of n comma Q is less than or equal to EX of n comma R, and that's less than or equal to EX of n comma P plus EX of n comma Q. The interesting part of this inequality, again, is the right side. The left side is immediate from the fact that we noted much earlier, which is that if the matrix Q contains the matrix P, then EX of NP is less than or equal to EX of NQ. In this case, we're applying it twice because we're saying that R contains P and R contains Q. So EX of NP is less than or equal to EX of NR. EX of NQ is less than or equal to EX of NR. So the maximum of EX of NP and EX of NQ is less than or equal to EX of NR. So we get the left side immediately. So that side, not interesting again. The right side is the interesting side. So for the right side, let's talk about why that is true. We want to show that EX of NR is less than or equal to EX of NP plus EX of NQ. To show that, it suffices to consider an n by n 0-1 matrix that has more ones than that. So a matrix that has at least EX of NP plus EX of NQ plus 1 ones, and show that it must contain a copy of R. So if we can say that any matrix with more ones than that has to contain a copy of R, then we can say that EX of NR is less than or equal to that. So we'll suppose that A is an n by n 0-1 matrix which has at least EX of NP plus EX of NQ plus 1 ones. I just want to note right here, there is an at least there, an annotated at least, but it is there. And like I said, the strategy here, we're going to try to show that if you have more ones than the bound we're trying to get, the bound right here, the one that we're trying to get, we have more ones than that because we have at least that plus 1, many ones. So we need to show that if we have too many ones, we contain the pattern that we're trying to avoid. So we need to show that this matrix A with too many ones contains R. First thing we're going to do is we're going to note that if we have EXNP plus EXNQ plus 1 ones, then we have more than EX of NP ones. So this matrix A, since it's an n by n 0-1 matrix, it has to contain P because it has more than EXNP ones. So we can consider that copy of P in the matrix. So we have this matrix A. We have a copy of P in there. And we can take its bottom right one, the bottom right entry. And in that copy, we're going to modify A. We're going to turn that bottom right entry to a 0. So I crossed through the 1. It became a 0 now. And we can note that if EX of NQ is greater than 0, then that means that EXNP plus EXNQ plus 1 is greater than or equal to EX of NP plus 2. So if we remove a 1 and the number of ones is still at least EX of NP plus 1, since it was at least EX of NP plus 2 before, we still can find a different copy of P. And it has to have a different bottom right entry because the bottom right entry of the copy of P that we found before, we changed that to a 0. So we can repeat the process of finding copies of P and then changing their bottom right entries to zeros in the matrix A until we have EX of NQ plus 1, distinct bottom right entries of copies of P and A. So we can do this process a total of ex of nq plus 1 times. And that's because our matrix A has at least ex of np plus ex of nq plus 1 ones. And each time we repeat this process of finding a copy of P and changing its bottom right entry to a 0, we're only removing a single 1 from our matrix A. We're only changing a single 1 to a 0. So if we start with ex of np plus ex of nq plus 1 ones, we can remove a total of ex of nq plus 1 ones until our matrix A only has ex of np ones left, and then we can't guarantee any more copies of P at that point. But all we need is the ex of nq plus 1 distinct bottom right entries of copies of P and A. And that's because ex of nq plus 1, if we have that many ones in an n by n matrix, we're guaranteed to have a copy of Q in the matrix. So in our matrix A, here's our matrix A again. We know that it must have a copy of Q somewhere. So here's a copy of Q. And even more specifically, this copy of Q is a copy of Q on the bottom right entries of P. So the bottom right entries that we found in the copies of P and A, the ones that we turned to zeros, this copy of Q is on those bottom right entries. Because the total number of those bottom right entries was ex of nq plus 1. And we're guaranteed to have a copy of Q if we have at least ex of nq plus 1 ones. Because ex of nq is the most number of ones we can have in an n by n matrix that avoids Q. So since we have more ones than that, we have to contain Q. So these are bottom right entries of P that we found. So we found a copy of Q on these bottom right entries of P. What does that mean? Well, this one right here, this one that we see, that one's a bottom right entry of P. This whole copy of Q is on bottom right entries of P. So that one has to be a bottom right entry of P. So we can just draw the P there. So there's P. And let me draw that P a little better so it actually fits in the matrix A. So there's our copy of P right there. So we have the copy of P right there because that one was a bottom right corner entry of a copy of P. So there's the copy of P whose bottom right entry it was. And then we have the copy of Q, we said, the one we found because we had at least ex of nq plus 1 ones. And down here, it doesn't matter what's down there. That can be anything. And right there, we have a copy of R. So we have a copy of R in A. And that means that we finished what we were trying to do. So we assumed that A was an n by n 0, 1 matrix, and it had ex of np plus ex nq plus 1 ones, at least that many ones. And our goal was just to show that A contains R. And we just did that. We found a copy of R. I just want to note again, it doesn't matter what's down here or what's here, because to make a copy of R, for A to contain R, we're allowed to change ones to zeros. So if there's any ones in that bottom left corner or the top right corner, we can change them to zeros. And our matrix R, the matrix R, recall that it's created by overlapping P and Q at those corner ones and putting zeros elsewhere. So zeros out here, P and Q there, that was our R. So whatever is in these bottom left or top right corners, it doesn't matter what the entries are because they can be turned to zeros. And those are the entries in the bottom left and top right of R. So we have a copy of R in A. We have the A contains R, and that's what we wanted to show. We just want to show that A contains R because A had too many ones. So to avoid R, we must have fewer ones than that. We must have at most ex of np plus ex of nq ones. And that's how we get this upper bound. So that's all we have to prove to show this whole operation. So before the end of this video, I have one more problem for you to think about. And this problem, it's nice in a way because you can apply multiple of these operations. You don't have to use multiple of them, but there's multiple ones of them that you can apply to solve this problem. So you can choose which one you want to apply. Not all of them are going to work on it, but multiple of them will be helpful. So here's the problem. And in order to state the problem, I just want to use this notation. So the identity matrix, I sub k, it's going to denote the k by k identity matrix. So we saw I sub 2 earlier, I2 right here. It's a 2 by 2 identity matrix. The identity matrix just has the main diagonal is 1s and all the other entries are 0s. So let me draw I3. And we can keep on going like that. So the problem for you to think about, prove or disprove that the extremal function ex of n comma ik is bounded between k minus 1 times n and 2 times k minus 1 times n for all k and n greater than or equal to 1. And that brings us to the end of this video, but we'll talk more about extremal functions of 0-1 matrices in the next video. Thanks for watching.